Okay, so 11.11 is on applications of Taylor polynomials. Okay. Now, last time I gave you a definition, but we didn't really use the definition. We didn't use the inequality. Okay, so let's state it one more time. Taylor's inequality says that if f of n plus 1's derivative of x is less than or equal to some constant m for x minus a is less than or equal to d, then the remainder, okay, r sub n of x satisfies the inequality absolute value of Rn of x is less than or equal to m over n plus 1 factorial absolute value of x minus a to the n plus 1, okay, for x minus a is less than or equal to d. Okay, so what this gives me is this gives me an upper bound, okay, an upper bound, okay, on the remainder of my power series. Okay, so okay, it's really the remainder of my Taylor polynomial. Okay, so you know the function itself. Okay, remember f of x is equal to Tn of x plus Rn of x, right? Where this was the Taylor polynomial. And this is the remainder. Right, so we call that the remainder function if you want. Okay. Okay, and so we want to know, okay, how close are our approximations? How good are they when we approximate functions with a Taylor polynomial? So let's look at that. Let's look at approximating functions. Okay, so let's approximate a function and see how good it is at approximating. Okay, see what the error bound is. Okay, approximate the function f of x is equal to the cube root of x by a Taylor polynomial of degree 2 at a equals 8. And find the accuracy of this approximation right, for x is less than or equal to 7, or sorry, x is less than or equal to 9, but greater than or equal to 7. Okay, x is between 7 and 9. Okay, inclusive. Okay, so let's create our Taylor polynomial for this. Okay, using what we know how to generate a Taylor polynomial. That's the summation of n equals 0 to infinity of fn of x, nth derivative of x. It's actually at a, sorry, nth derivative evaluated at a over n factorial x minus a to the nth power. Right, so this will get me a Taylor polynomial. Okay, it'll actually give me a Taylor series. The Taylor polynomial is when I actually just go to n. Okay, so we want to stop at degree 2, right? So we want this to actually go from n equals 0 to just 2. Okay, and that will give me my Taylor polynomial of degree 2. So we want 3 terms. We want the 0 term, we want the 1 term, okay, and we want the first term, and we want the squared term. So this is going to end up being a quadratic. Okay, so let's get some our derivatives. Okay, so we want our function, obviously. Okay, f, okay, of a. Okay, well, let's just do f of x first. It's easier. F of x is equal to the cube root of x, which is equal to x to the 1/3 power. Okay, so f prime of x is going to be bring down the 1/3, and this gives me x to the negative 2/3 power. Okay. F double prime of x is going to be negative 2/9 times x to the negative 5/3. Okay, and now what we want to do is we want to plug in our a equals 8. Okay, I evaluate this for 8. So f of 8 is going to be 8 to the 1/3 power, which is just 2. Okay, f prime of 8 is going to be 1/3 times 8 to the negative 2/3 power. Okay, well, 1/3 of 8, okay, 8 to the 1/3 is 2. And so if I kind of break it up like this, 1/3 times 8 to the 1/3 to the negative 2, then I know that 8 to the 1/3 power is just 2, because that's the cube root of 8. Cube root of 8 is 2. So this becomes 1/3, 2 to the negative 2nd power, which is 1 over 2 squared, which is 1 over 4 times 3, which is 1 over 12. Okay. Okay, f to the double prime of 8 is equal to negative 2/9, okay, times 8 to the negative 5/3, and we can do that little trick again of just saying that's 8 to the 1/3 to the negative 5th power. Okay, so this is going to be negative 2/9 times, this is 8 to the 1/3 is 2. 2 to the 5th power is 32. So that's 1 over 32. Okay, and so this becomes, cancel, that's 16. Negative 1 over 144. Okay. Now we're gonna say, okay, well, this is f of x is equal to, okay, now that I have my derivatives evaluated, let's write out the first 3 terms of this series. Okay, f of x is going to be equal to f of 8, okay, over 0 factorial times x minus a to the 0 power, plus f prime of 8 over 1 factorial times x minus a to the first power. Okay. But again, what is A? A is 8, right? So we can plug the 8 in there. Okay, and then plus f double prime of 8 over 2 factorial x minus 8 to the second power. But we've already figured out what these numbers are. Okay, f of x is equal to f of 8 was 2. So this is 2 over 0 factorial x minus 8 to the 0 power, plus f prime is 1/12, so that's 1/12 divided by 1 factorial times x minus 8 to the first power, plus this is going to be f double prime of 8, which is negative 1 over 144 over 2 factorial x minus 8 squared. Okay, and so this becomes, this goes to 1, this goes to 1, and so that just becomes 2 plus, okay, and this is going to be 1/12 divided by 1 is just 1/12 times x minus 8, plus 2 factorial is just 2, so this thing really becomes like a 2 over 1, and I can flip that upside down, so this becomes negative 1 over 288 times x minus 8 squared. So here's my approximation. Okay, this is approximately the cube root of 8, or sorry, the cube root of x. But it's only valid between 7 and 9, because I said in the beginning it was only valid between 7 and 9. I want to know how close of an approximation is this polynomial to this, weird cube root function. How close are we? Right? So, at 8, we're going to be exact. It's going to be 2 and 2. If I plug in 8, f of 8, I'll get 2, and the cube root of 8 is 2. So they're going to be exact at 2, but I want to know how close am I? Like, what's the error that I'm going to get within this region? Okay, so maybe if we go back to Desmos and we see what we're looking at. So I want to type in, okay, y equals, okay, 8, or not 8, I want x. Go back. I want x, and I don't really have a cube root here, so I'm going to just go x to the 1/3 power. Okay, and that gives me my cube root function. Oops. Okay. And so, but where were we centered? We were centered at 8. Okay, we were centered at 8. Okay, so maybe I'll put in that point 2, 8. 2, or sorry, 8, 2. 8, 2. Boom. Okay, so there's that point. 8, 2. I can label it if I want. Okay, well, that's our center. We're centered around that. And so we want to know, well, how good of an approximation is this? But we only care about how good of an approximation the polynomial is that we attained within certain region. And that's between 7 and, okay, 7 and 9. So I'm going to put that in there. I'm going to put in x equals 7. Okay, give me these boundaries. X equals 7 and x equals 9. Okay, so in between these boundaries, I want to know how good of an approximation was, the Taylor polynomial. Okay, sounds good. Okay, so let's plug in our polynomial and see how well we did on approximating this cube root function with a polynomial with a quadratic that we came out with. Okay, so we only went out 3 terms, so you would think that it's not going to be very accurate. Okay, that's what my assumption would initially be. So we did 2 plus 1/12, okay, times x minus, okay, minus 1/288 times x minus 8 squared squared. Ooh, look at that. Okay, how far off are we? Well, it's in between 7 and 9. Okay, in between 7 and 9 here. Yeah, the lines are almost indistinguishable. We kind of have to go out pretty far. Okay, maybe not that far, but we go out pretty far from now. Now the range is 0 to 25, and that parabola, okay, it obviously doesn't follow the curve over here, that 0, that it fails to curve like that. But in between 7 and 9, it's really hard to tell that there are 2 different lines there. And I mean, I would have to zoom in really, 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 really far. Ooh, there we go. Really far. Let's zoom out a little bit. Let's go to 7 exactly and see how far we have to zoom out. There's 7, right? So let me put some dots here. That's one of the intersections. So you can see, like, oh, okay, we have 7 and 1.9132. That's for that intersection. Give me the other intersection, will you? I don't know what's gonna give me the other. Yeah, there we go. And we have 7.1132 and 7.1929. So a very close approximation. Okay, it's only, and we're accurate to, almost within 2 decimal places, 2 decimal place accuracy. Okay, and almost to 0.003. Because if I subtracted 32 minus 29, I would get 0.003. So very close. Okay, it's within 0.003. Okay, so let's work with this and see, yeah, what's the error bound on this guy? Okay, so for R2 of x, the remainder, or the error bound on the polynomial, okay, it's less than or equal to m over n plus 1 factorial. I'll just do it, or I'll rewrite the inequality. This is Taylor's inequality. X minus a to the n plus 1 power, right? Pretty sure that's what that is. Yes. Okay, and what's m? Well, m is less than or equal to f of m plus 1 derivative, I think that's absolute value, of x is less than or equal to m. Is less than or equal to some boundary there. Okay. Okay. So let's plug in what we know. R2 of x is less than or equal to m over 3 factorial times x minus 8 to the third power, where m is less than or equal to the third derivative of x, which is, oops, it's not, this should be the other way around, I'm sorry. This guy is less than or equal to m, not the other way around. No. Okay, so the third derivative is what I'm looking for. Okay. Okay, so what was f of x? Well, f of x was, again, x to the x to the 1/3 power. We already found the first two derivatives. The first derivative was 1/3 x to the negative 2/3. The second derivative of x was 2/9, negative 2/9, x to the negative 5/3. And then if I bring it down again, this just becomes 10/27, x to the negative 8/3. Okay, f triple prime of x. Okay, now we're saying that this is less than or equal to m. Well, how do we get this guy to be less than or equal to a number? Okay, well, we'd have to plug something in for x. And what we do, okay, is we plug in our endpoints. Okay, where it's only valid on from 7 to 9, those endpoints. Okay, because that's the interval. Okay, so we're going to say that this is 10/27, okay, of x to the 8/3, but okay, we're going to plug in 7 to that, and we're going to plug in 9, and we're going to take the biggest one. Okay, the upper bound. Okay. Okay, so which one's going to give me the bigger one? Is it dividing by the bigger number or the smaller number? Well, it would be dividing by the smaller number. That would give me the bigger value, and that's what I want. I want the upper bound. So I'm actually going to plug in 7 there. Okay. So okay. So we can say that 10/27 absolute value x to the 8/3 is less than or equal to 10/27 7 to the 8/3 power. Okay, so that's going to be our upper bound. Because everything on that interval, on what interval? This interval here, on that interval is going to be smaller. It's going to be a smaller value than this upper bound, okay, for the third derivative. Okay, that's my upper bound. Okay. So let's plug that into our formula for m. We're going to say that R2 of x is less than or equal to, okay, 10 over 27, 7 to the 8/3 power, okay, divided by radical 3. I'm just going to multiply that by 1 over 3 factorial. Okay, divided by 3 factorial is multiplied by 1 over 3 factorial, which is 3 factorial is just 6. Okay, less than or equal to x minus 8 to the 3rd power. Okay, but what is the absolute value of x minus 8? Can we do anything with that? Well, yeah, this actually comes directly to us from the interval again. We have the interval 7 to 9. So the absolute value of x minus 8 is less than or equal to what our radius of convergence is. Our radius of convergence, which is 1. Now, how do I get that? Well, if I take 7 is less than or equal to x, which is less than or equal to 9, okay, and I subtract 8 from everything, then I get -1 is less than or equal to x, which is x minus 8, which is less than or equal to 1. And we can see that we can rewrite this as x minus 8 is less than or equal to 1, where our radius of convergence is 1. That's our radius of convergence. So we can say that this thing, okay, is less than or equal to 1 times 1 to the 3rd power. This is less than or equal to, that thing there is less than or equal to 10 over 27 times 7 to the 8/3 power times 1 over 6 times 1 to the 3rd power. Now, these aren't equal, but it's less than. Remember, we're creating an upper boundary, right? So we're saying that everything, all of the values between 7 and 9, if I plug them in here, if I plug all those values in there, it's going to be smaller than if I just plug a 1 in. Okay? It'll be smaller than or equal to if I just plug a 1. That's going to be my upper bound. And so now I have a number with no variables. And I can say that this is less than or equal to, okay, let me cancel this out, 5 and 3. Okay, this is going to be 5 over 81 times 7 to the 8/3 power. Okay. Okay, and so R2 of x is less than or equal to this. Okay. And so what is that approximately? R2 of x is less than or equal to 5 over, well, let's do it less than or equal to approximately. Let's plug that into our calculator and see what we get. 5. We got 5 over 81. Let's not forget the parentheses. 81 times 7 raised to the 8/3 power. Okay, parentheses equals, this is 3.442 or if I round 3.443 to the negative to e to the -4th. That just means times 10 to the -4th. That means that I'm going to have 3 zeros in front of there. So this is going to be approximately 0.00034443. Okay, and so if I want to round, okay, for finding an upper bound, we always round up. even if the number is lower, the reason is because we don't want to cut off, we don't want to truncate, right? Because if I just rounded to this value here, well, I could actually get a value that's bigger than that because I cut it off. But if I go to the next one, okay, if I round to the next number up always, then it will include anything that comes after. Does that make sense? So regardless of what comes after, we always round up. If we round, we always round up because that's going to include anything that could have trailed. Does that make sense? Like 50 is bigger than 43, but 40 is not bigger than 43. Hopefully that makes sense. Okay, so we can have 50 because that's an upper bound, right? 50 is bigger, so that's our upper bound. And so we can round to this and say, okay, R2 of X, okay, now is less than or equal to, okay, less than or equal to 0.000345. Okay, so our approximation, so we can say our Taylor polynomial is accurate to 0.000345. Boom, which is pretty accurate, okay? But only when? Between 7 and 9. It's that the accuracy is only that accurate between 7 and 9. Otherwise, it's not very accurate at all. If you go from 0 to 1, this thing fails phenomenally. Okay, but between this interval, it actually proves to be a fairly accurate approximation. Okay, let's do another one of these. Okay, number 2. What is the maximum error for the sine of x? Oh, let me drop a line here. The sine of x equaling x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. When, okay, when x is between negative 0.3 and 0.3. Okay. So we're looking for the remainder again. Okay, we want to know how accurate is this thing. So we need to do some analysis here. Okay, first, it'd be nice to find out, well, what's A? Okay, what is A equal to? Can anybody figure that out? What would A be equal to? What type of series is this? Is this the Taylor series? Or is it a Maclaurin series? Where are we centered? Where are we centered on this one? Wouldn't this be absolute value of x minus 0 is less than or equal to 0.3? Right? Right? So where are we centered? Why aren't we centered at 0? Yeah, A is 0. And what do we call things that are centered at 0? Yeah, this is the Maclaurin series. For sine x. Okay, but we only went out 3 terms. Okay. So you would think that, okay, I went out 3 terms, then this would be easy. This would just be R2 of X again, right? Except it's not. It's not R2 of X. Okay, because we don't get all of the terms here because there are some terms that have coefficients of 0. Okay, so it's not R2 of X like we had before where we had 3 terms, right? In the previous example, we had 3 terms because we had, n was 2, right? So degree 2, polynomial of degree 2. But what do we have here? We actually have a polynomial of degree 5. Okay, so you would think that it would be, R5, right? R5 of X. Right, because we have degree 5, and you would be wrong once again. So sorry. Okay, you're just like, Alrighty then. So let's write out some terms here so that we can figure out what we're doing. Okay, we have the Maclaurin series. This guy here, and so why are we getting these terms, and where did the other ones go? Right, so if we have the sine of X, we get f of 0, right? F of 0 plus, okay, f prime of 0 times X, right? All over 1 factorial, all over 1 factorial. Okay, which is just 1. So we'll just keep going. Okay, for the Maclaurin series, and this is f double prime evaluated at 0 over 2 factorial, right? X squared plus f triple prime of 0 over 3 factorial X cubed. So what's happening? What's happening with, where did all these the even terms go? Well, the thing is that when I take my derivatives, right? Remember, if we go f of X equals sine X and f prime of X equals cosine X, okay, the sine of 0 is 0. F of 0 equals sine 0, which is 0. So this thing goes to 0. So we actually got rid of a term, okay? But the term is still there. It's still very much included in our remainder formula. Okay, it is a 0, but it's still there. Okay, think of this as like, this is like x to the 0 power, and this is like x to the first power. Even though the constant or the coefficient is a 0 and it wipes it out, okay, it's not gone. Okay, it is a term. It is a valid term. So we're actually out to the 5th term. However, when we do the 4th derivative, 0 over 4 factorial x to the 4th, I got to go out a couple more terms here, plus f to the 5th derivative of 0 over 5 factorial x to the 5th, plus f to the 6th derivative of 0 over 6 factorial x to the 6th, plus I'm going to go out one more. It'll fit on the page, trust me. Okay, f of 7, 0 over 7 factorial x to the 7th. Okay. Okay, and this is the plus dot 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 forever. It just goes on forever. Okay, so here's the deal. The deal is that every other one of these goes to 0. That goes to 0, that goes to 0, that goes to 0. Okay, and so what I'm left with is I need, is that R2 or R3? No, it's R2, right? Yeah, Rn is less than or equal to no, that's correct. Yeah, yeah. Okay. So for my remainder, it says this. It says R of n, right, of x is less than or equal to m over n plus 1 factorial x minus a to the n plus 1 degree, right? So the problem is that I need this to not be 0, not be 0. I can't have that be 0. I don't want this to be 0 either, not 0. I don't want that to be 0 either. Okay, I can't have these be zeros. Okay, so if I did R5, if I did R5 of x, what would I have to do? I'd have to go m over n plus 1 factorial x minus a to the 6, right? These n plus 1s would be 6. Okay, but there's a problem. My function, my nth derivative, which would give me my m, right? Because how do I get my m? I get my m by going fn plus 1th derivative. My 6th derivative gives me my m of x. This thing is 0. That equals 0. So that m there is going to wipe everything out if n is 5. So I can't use 6 to get 5. Okay. What I have to do is I have to go to 7. I have to go to 7 to get 5, or to actually get 6, because I'm just adding 0 onto my next term. So it really doesn't change anything. So I actually have to go to the 7th term to get the bound for the 5th term. Okay, I have to go to the next one that is, okay, but we don't write it as R5, we write it as R6. Oops. Boy. Oh, it exited out for some reason. Okay. So the way we write this is we say we go R6 of x, because that's going to allow us to use an m of the 7th derivative, or f7. Okay. And so what are we going to, what is f7th evaluated at 0? What is that guy? Well, let's just follow the pattern. Okay, the pattern for sine. What is the pattern for sine? Okay. So what is this going to be? This is going to be R6 of x is less than or equal to m over n plus 1, which is 7 factorial, x minus 0 to the 7th power, okay? Where m is less than or equal to f of the 7th derivative of x, which is not equal to 0, okay? So if it was 6, it would be equal to 0. Let me do it like this. 6 derivative of x is equal to 0. Boom. Which I don't want it to be 0, because the error is not going to be 0. Okay, the error needs to be some value that's above 0. Okay, but if again we look at the sine function, the sine of x, we get 0 plus x, okay, minus, or sorry, plus 0 minus x cubed over 3 factorial plus 0 plus x to the 5th over 5 factorial, okay, minus, or sorry, plus 0 minus x to the 7th over 7 factorial. Okay, so what was my 7th derivative then? Evaluated at 0. What is f7 evaluated at 0? Okay. Okay. It was -1, and so how would I get -1? I mean, I really didn't want to have to write out all 7 derivatives, but I will. You know, they're just going to oscillate. It's going to go sine x, cosine x. This is 0, 1, 2, 3, 4, 5, 6, and 7. I guess it's not that bad. Okay, negative sine x, negative cosine x, and then back to sine x, and then cosine x, and then negative sine x, and then negative cosine x. So the function is negative cosine x, right? Okay. So f of x, or sorry, the seventh derivative of f of x is equal to negative cosine x. Okay. Okay, so we want to absolute value that. Okay, and try to get a boundary for that. Well, right, because we want this guy in here. Okay, and get, oh gosh, I wrote it backwards again. I keep doing that. I'm so sorry. Okay, we want to get an upper bound for that. Okay, so what's the absolute value of negative cosine of x less than or equal to? Well, this is going to be the absolute value of cosine. And what do we know that the absolute value of cosine, what do we know about the cosine function that it's bounded by? What is the cosine function bounded by?
1.
Yeah, 1. It's bounded by 1 and negative 1. Thank you so much. Okay, this is bounded by 1. So that has to be, okay, so m is less than or equal to this, which is less than or equal to 1. Is that right? Nope, the other way around. Is that right? Let me make sure. I'm getting messed up with my, yeah, that's right. Okay, so this, okay, is less than or equal to m. And so what can we make m? Well, we can just make m 1. M equals 1. Okay, so we're going to plug in a 1 here. Well, that makes things nice. Okay. So let's bring this down. This r sub 6 of x, okay, of less than or equal to m over n plus 1 factorial, okay, x minus a, n plus 1. Okay. So again, let's plug in what we know. We know that m is now 1. We know that n is 6. So that's 6 plus 1 factorial. This is 6. We know that a is 0. Okay, and we know, again, that m is 1. So it's going to be 1 over 7 factorial. Okay, times the absolute value of x to the 7th power. Okay, okay. But now, what do we know about the absolute value of x? Based on our interval. Remember, it was from 0.3, negative 0.3 to 0.3. So the absolute value of x is less than or equal to 0.3. Oh, okay. So then you're telling me that this thing, okay, r6 of x is less than or equal to everything in the function, this function, but this function, this absolute value of x, that's bounded. So this is going to be less than or equal to 1 over 7 factorial times 0.3 to the 7th power. Okay, so now this is going to be equal to 1 over 5040 times 0.3 to the 7th power. Okay, so let's plug that in to our calculator. Okay, calculation, please. I'm coming. Okay, so let's do 1 over 5040. Okay, enter that, times 0.3 raised to the 7th power. Okay, that's 4 point, and I'm gonna round up. I'm gonna go 4.4. Okay, because I want an upper bound, not something that could be slightly, near it. Okay, I want a complete upper bound. So I'm gonna go 4.4 times 10 to the negative 8th power. Okay, that's 2 4s with 7 zeros in front of it. So extremely small number. Extremely small number. So this is approximately, okay, 4.4 is actually, I'm going to do the inequality because I rounded. It's less than or equal to 4.4 times 10 to the negative 8th power. Okay, because I rounded up, I can put the inequality instead of, some, approximation. Okay, so it's less than or equal to, so what did we found our upper bound? Okay, so this is, so we know that sine of x equaling x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay, we know that this thing is accurate to within 0.000000, is it 7? Yes. Okay, 4. Okay, so we got 7 zeros in front of the 2 4s. Okay, is accurate within that, okay, in the interval from negative 0.3 to 0.3. Okay, so how accurate it is? It's pretty accurate. It's within, it's accurate to 7 decimal places. Right? So what does this look like if we were to graph it? Okay, so again, we've got sine x, right? Oops. We've got sine x. Okay, I gotta zoom out of that. Let's do trigonometry. Let's see if we can get more options. No. I was hoping that it would do a trigger thing, but that's okay. Okay, we'll just zoom in a second. I want to get rid of these values. Okay. There we go. That's better. Yeah, let's start with a 1 by 1. That'll be good. Okay, so I want to plug in y equals sine x. Oops. Okay, so we have y equals sine x. Okay, from 1 to negative 1. We can see this is a sine curve. Okay. But I want to zoom in. Okay. From 1 to negative 1, because I'm really interested in what's happening between negative 0.3 and 0.3, right? So let's plug in our Taylor polynomial of what? X minus x cubed over, whoops, okay, over 3 factorial, which is 6. Okay, and then plus x to the 5th, okay, over 5 factorial, which is 120. Okay, and then we want to know, okay, well, how accurate is this, right? So we have this blue polynomial, this 5th degree polynomial, and we want to know, okay, how accurate is it, between negative 0.3 and 0.3. So between negative 0.3 and 0.3, which is trying to get it on the graph there, they're almost indistinguishable. Okay, that's very accurate, extremely accurate. I'd have to zoom in. Again, I'd have to, if I wanted to know, like, what's the bound here? Okay, I could zoom in on these boundaries and I would have to take the bigger one, okay, of them. But yeah, I mean, it's extremely accurate. I probably couldn't, it would take me a long time to zoom in to 0.00000007, but you could do it. Okay, but they're essentially the same between those, within that boundary. Within that.
I think I read something that like these Taylor approximations are actually what the calculator uses. Is that right?
No, what the calculator is doing is it's just taking a value, a very small value, and it's calculating that value over and over again, and then it's just plotting and if the pixel lines up with where that occurs on the calculator, then it'll plot a pixel within that region. Okay, so if you think about computer
No, I
science,
mean I thought I read something like when the calculator gives you a value of sine for a number, like it's doing a Taylor approximation to come up with that value.
yeah, I think that's more. I mean, it's possible. It depends on how they program the calculator. For these functions. I don't know how they are. Maybe they are, for all these functions, they're just throwing in the Taylor polynomial. Or it would be the Maclaurin, right? So the Maclaurin for them, but I would think that that's a lot more work than just taking and calculating it. Yeah, I don't know how they would calculate it. I guess they would. Yeah, I guess you're right. They would have to, because they have to use the limits of the. Yeah, I mean, I don't know. I mean,
Yep.
been doing this for what, about 100 years, so I don't know exactly how they're programming it, but that makes sense. That would make sense.
Yeah, I was just curious, and then seeing how accurate you were able to get with just 7 iterations or seven derivatives. If the calculator goes out to like 20 derivatives, then they would have the actual value.
Right, exactly. I mean, how close do you really want to get? Right. I mean, that again, the calculator only goes out, 13 or 14 digits, and then it stops. And you can see that if you take something, you divide, and then you multiply by, say, 10 to the 10th power, it doesn't carry digits. It'll just give you zeros after that. It rounds once and then carries the zeros. Because it doesn't have an infinite memory to carry all those digits forever. So at some point it truncates, and it depends on, I guess, how fancy your calculator is, depending upon, where it truncates. But I could see it using, yeah, I can see it using a Maclaurin series for sine and cosine. But you again, like we showed last time, you can get the cosine by just taking derivative of the sine. So, I mean, and I don't know how the calculator is getting derivatives and all that stuff. I mean, I know how I would do it, but I leave that up to the programmers. But yeah, it's a good question. It's a good computer science application. So, but where this is really handy is where you get to Fourier series and Fourier analysis, where you have to combine sine functions together. And so you can turn them into Taylor polynomials or Taylor series, and then combine them term by term, and then turn them back into a, some function of sine. So, and then you can use those sine waves to approximate any curve, any curve that you want to. So, yeah, that's Fourier analysis, which is it's a whole other, it's part of math. So it's a whole other field, a whole other field of mathematics. But they're good in describing waves and on light and heat and anything that comes in a wave. So, okay, that's it for chapter 11.